Okay. Good afternoon, everyone. Thanks for joining us. My name is Tony Glay. I'm a remote sensing specialist with the Wheatland Geospatial Lab. And this afternoon, we're fortunate to have Paul Smitherman from the Fogler Library and Dave Sandilands, our very own Dave Sandilands from the Wheatland Lab, to talk about the Sewell Company photo collection at Fogler. So Paul Smitherman has been studying and working at UMaine since 2002. During that time, he has earned a bachelor's in physics, a master's in spatial information science and engineering, and has been involved in numerous research projects on campus. He is currently a library specialist at Fogler Library, where he is a technical advisor in the Special Collections Department, developing solutions to the challenges that archives face in the digital world. Dave Sandilands has been with the Wheatland Geospatial Lab since its inception, earning an MS in Forest Resources in 2017, continuing with the lab as an aerial survey pilot and remote sensing technician. He is responsible for the planning and implementation of aerial survey flight missions and image processing workflows, and is involved in several of the lab's ongoing LiDAR and photogrammetry-based research projects. Dave brings his professional aviation experience to the Wheatland Lab, having earned a BS in aviation from Downing College in 2002, and is an FAA licensed airline transport pilot, certified flight instructor, and Part 107 remote pilot. With that, I'll turn it over to Paul.
Hi, it's very nice to be here today. Thanks for having me. It's I'm Paul Smitherman, and I work at Fogler Library, like Tony said. Been managing the Sewell collection since we got it about 2 years ago. Picture here is Bangor 1965. We have a bunch of these on Digital Commons. This is actually one of the most popular ones. So like Tony said, I have a EAMS around here. I did some research back in the before time. I did a lot of statistics with GIS. This is radon and uranium on bedrock in the greater Augusta area. And we're making some models of that. I don't have a lot of experience with photogrammetry surveying, so I started learning that the last couple of years. So it's really interesting. I work at the library now. This is the library here, looking up north. Field house, you can see 1950. The wing wasn't on the library at this point. Over here, I think this is where the unit is now. A lot of really interesting things you can find in the collection. So yeah, one thing I do other things too. One of the big things I do is I handle the Sewell collection. I have a sample of about 1,200 of these images online at our Digital Commons, and there's pretty much something from every county out there. Just to take a look. There's really a lot of fun. There's some gems in there that people can find. A little bit about the Sewell Company. Founded in 1880. They began offering the aerial photography services in the 1940s, and they were sold to a larger investment fund in 2018. This is actually one of the earliest photos here that I have. This collection, 1946. There's quite a bit of stuff in EMP, I think, is stuff from main power. So after the company was sold, they decided that they couldn't maintain this large collection of analog photography. And so the library received those in October 2019. There's about 3,000 rolls of film, about 1 million photographs there, approximately 1946 to 2015. This is what they looked like in the basement of Sewell before they came over. So it's a nice photo by Brett Beauregard. And now they're housed at our climate control storage facility. happily there now. How do you access these? Well, the small portion of the collection was actually digitized at school, maybe about 2.5–3% of the entire collection. So I've got, like I said, I've got about 1,200 of these up on Digital Commons. If you search, say, school company or photographs, our Digital Commons site is, I think, pretty much the first one that comes up. And as for the others, I saw quite a few that are already digitized, but I haven't put up, so I do requests on those. If they haven't been digitized yet, but now I can do limited number of photos using this scanning setup. But I can do it for specific locations. So if you have a specific location, let me know, and I can typically do, one photo, one on either side, two on either side. Takes me about a week to get those out. So just let me know if you have an idea. I can't do like large sets of say 30 or 40 images at this point, but we're trying to get them, like I say, we're trying to get these digitized at this point. And today you're going to be seeing a sample of that was provided by the SRI. We actually have canonical film rolls started at #1. There are some rolls before that, but this is from roll #1 down at the top, 1940. It's kind of interesting to see the horizon. So some of the applications we're seeing with these, one of the things I like to do is look for clouds in the water, but that's another story. Like urban history, interesting stuff. This is a Bangor Mall with the construction, 1977. 1953, people were often interested in trying to determine whether a particular building was or was not there, or roadway, or a lot of things with easements and things like that. Technology history, this one with Navy Yankee. In this Bassett, 1972, right after it was built, but before it went online. That was just decommissioned in 2004. And tore down the building and everything. Yeah, this is the tunnel that cut with just in China, 1966. A lot of different kind of interesting technologies. The antennas are huge. You can see the shadows of the antennas. One over here for today is forestry wood products. We have extensive collections. It was, for example, a survey by the Great Northern Paper in 1953. And a lot of other companies that they SD1. Number of them. And then we have the Mill in Old Town now in paper. This was launched by Chemical Fiber Company. Full swing. The dam is there. The dam, I don't know. I can't remember when they took the dam down. I think within the last. So if you have any questions, comments, any other requests, just send me an email. I'm usually over there 5 days a week, so send me an email. See if I can help you out. I don't say thanks to our partners at the SRI for providing the sample roll. They did the scanning and processing of the roll 1189, which Dave is going to show you here shortly. And sometime on the horizon, Tony and Dave alerted me to the fact that there was a file cabinet in their lab that had a bunch of YouTube photos in it from NASA. I think it's 72. So I'm looking at those. These were used for calibration and their research ahead of the first Landsat. So I think they were trying to, I think calibration, but they also just wanted people to see what high altitude photos look like too. Anyways, that's about it for me. I went fast, but when I have plenty of time for Dave to get up here. So, show us where it's at.
All right, thank you, Tony and Paul. And very good afternoon to everyone. So when Paul gave a talk introducing the Sewell collection earlier this past year, I thought it would be really interesting to experiment with some of the techniques that we use for more modern digital photography and see if they can be applied to these historical photos. And if I could even generate, geospatial 2D and 3D map products with a reasonable expectation of accuracy. And also, could it be done with a minimum investment in time and effort and a minimum software investment to make this technology accessible to the average GIS user that may have little to no experience with doing this? I'm not inventing anything here. This certainly has been done before with historical imagery, but I really wanted to see if it could be done with this specific collection at the different scanning resolutions that we have available to us, and what we can generate with our local data here that we have available to us. This isn't tied to any specific research project or anything like that. This was primarily done just out of my own curiosity. So what I propose for today is I will start with a brief instructional bit where I'll describe what is digital aerial photogrammetry, how can we use it, what are its limitations, and I promise to do this using as many visuals as possible, and I won't be getting into the equations or digging down into the algorithms or anything like that. And since I'll be making comparisons to LiDAR, there's an expectation that there's at least familiarity with what LiDAR is and how it can be used by the audience, at least on a general level. So I'll explain the basic digital photogrammetry workflow using a demo. And then I'll dig into the specific Sewell collection that I chose, looking at different methods, comparing how the film rolls were scanned, as well as different pre-processing steps to get the photos ready to bring into this workflow. So digital photogrammetry, we perform a form of it called photogrammetric structure from motion, or SFM. This is sometimes also referred to as FODAR or photogrammetric LiDAR, because FODAR is structurally very similar to LiDAR with the same data file formats used. And now for a few definitions, and I'll have some visuals that demonstrate how all of these concepts work in a couple of slides to make things a little more easy to understand. But the definition of structure from motion is an application within the field of computer vision for recovering the 3D shape and appearance of objects from partially overlapping images. Computer algorithms then identify image features with geometrical similarities and trace the movement of these features points across a series of image pairs. This is also known as feature matching or image correlation. So once feature points are matched across image frames, the position and orientation of each frame relative to the others and the sensor can be determined. Through a process of triangulation, a data file is created known as a 3D point cloud that has X, Y, and Z coordinate locations tagged to each and every point. And you can also update those X, Y, and Z locations with real-world geographic coordinate information. So what data sets can be produced from 3D point clouds? We can map things, we can map spatial patterns across the landscape. This can include the form of a bare Earth surface or a digital elevation model, or DEM. You might also see this, the term digital terrain model, or DTM. They're typically referred to interchangeably. However, you do have to understand that there are some limitations if you're deriving these products from FODAR as opposed to LiDAR, which I'll discuss in a little bit. You can map roads, structures, and other surface features. Within the realms of forestry and wildlife management, you can map various vegetation metrics such as canopy closure and structure, tree and stand heights, again, understanding that there are some limitations if this is with FODAR. And you can predict some inventory metrics across the forest, like stand volume, basal area, above ground biomass. Again, like I said, there are some limitations. It's not a direct replacement for LiDAR. So the next couple of slides I actually borrowed from an existing slide deck that we have that was more geared towards folks who are weighing the decision of acquiring either structure from motion or LiDAR products. But the basic concepts of these pros and cons, I think, can be applied to the historical imagery as well. So for one, structure for motion products are available at a lower cost than LiDAR. Reduce investment in equipment. If you're talking about historical imagery, you do need to invest in a decent scanner to get good results. But they're also less computer resource intensive, so you can process these data with generally with a desktop computer or laptop. Quick mobilization and turnaround. So once you have those digital files in hand, depending on the size of the area you're working with, you can generally process them within a few hours for a small area, maybe a little over a day if you're talking about a rather large area. And there's a wider range of spectral information contained in FOTAR products compared to LiDAR. So that photographic information from the photos themselves is attached to each and every LiDAR or each and every point in the point cloud. So you can do things such as monitoring vegetation health, estimate forest age, map species composition, and even perform some subjective photo interpretation using your own knowledge of what different surface features should look like. And in this SFM example here, where LiDAR may have very well picked up all of the tree structures, it's that photogrammetric, that spectral information that we can look at and see that that white pine in the middle of that stand is not looking too good. So it's probably on its way out. So here's where some of those limitations come in. A camera is a passive optical sensor system. So unlike LiDAR, which can send its pulses down through the canopy and can recreate the structure within the canopy as well as the ground below, even if it's dark out, a camera, with what you get is what you see, right? So if you can't see the ground or it's obscured, then you're not going to be able to recreate the ground in your models. So if you want to extract relative height information, the ground either needs to be visible in the photos, or you have to pair your data set with a high resolution DEM, which you could either download from a GIS data catalog or generate from an existing LiDAR data set. This example here of a FOTAR point cloud up top, it's a pretty solid canopy surface, but you really can't see what's going on under there. So it's only when we bring in that high resolution DEM that we can now see the height of all of those trees throughout that data set. So this doesn't really apply to historical imagery, but it's hiding down there. Another key difference between LiDAR and FOTAR is that in FOTAR, that highly accurate geographic location information is usually not built in, and you have to go in and manually enter that as part of your workflow. So let's see if I can try and maximize the screen here so I'm not hiding too much. Not sure if I can do that at this point. So what are some considerations when you're comparing LiDAR-based versus photo-based DEMs? This example here, the top row, we're looking at a recreation of LiDAR points, and you can see they're pretty well distributed throughout the canopy and picking up that topography really well. So if you want to remove that topography and figure out what the actual tree heights are, it's pretty easy to do. In the next row down, looking at just FOTAR, you see that it picks up the surface of the canopy very well, but only a few points actually make it down to the ground. So the only way to figure out where the ground is really to estimate and interpolate a straight line between those points. And unfortunately, you're missing a lot of those holes and valleys there, so that when you try to remove that topography or normalize the data set, you end up with some trees that are taller than they should be and some trees that are coming in as shorter than they actually are. But on the bottom here, if you have access to a high resolution DEM, you can merge your data set with that, and now you can create a product that's comparable to what you would get with LiDAR. So as part of the SFM workflow, first step, you need to have overlapping images, right? So when we're talking historical imagery, generally we're talking about 60% overlap between consecutive photos, so from one photo to the next, and generally about 30% overlap between adjacent flat lines, so side to side. With more modern digital camera systems like what we're using today, it's more common to see a much higher percentage of overlap, typically around 80% end-to-end and side-to-side, and that does a really good job at recreating these three-dimensional models, where now you can view these objects on the ground from as many different perspectives as possible with the minimum amount of occlusion. The next step here, SFM algorithms identify and extract key features from within the imagery. That's done automatically. And that's then followed up with feature matching or image correlation, where that relationship between the same features on overlapping images is established. So now software knows that, say that feature representing the corner of the parking lot in the lower left image is the same feature in the other two images as well, and so on. So this process is then followed by what's called a bundle adjustment, where I'll just call it fancy math, builds the relationship between 2D photo image points and the sensor to create a 3D predicted point location. This also creates what's called a sparse point cloud. So this process also solves for the exterior and interior orientation parameters for each photo. That's what I have up top there next above those photo icons. And when we're talking about exterior orientation, we're referring to the pitch, roll, and yaw movement of the camera at the moment that each photo was captured. For the interior orientation, that's referring to the internal geometry of the camera, things like focal length and a variety of lens distortions that may be present. Generally, those parameters don't change from photo to photo. However, they may change from day to day depending on changes in atmospheric temperature and pressure and how the camera is handled and things like that. So you still want to account for that in your models when you're processing different projects. You can also append real-world geographical locations, X, Y, and Z locations to your sparse point cloud. So now instead of being in this arbitrary computer coordinate space, you have real-world space where you can start making measurements. So the next thing created is a dense point cloud, and this is where a depth map is generated for pixels from the original imagery. This more closely resembles what you would expect to see if you're used to working with LiDAR data. You can color this product by different ways, including by elevation here. But you get that added bonus of all that spectral information in the photos, so you can also color it by RGB if you wish to. Additionally, you can create some orthomosaics. They can be collections of hundreds, even thousands of your photos in your project area that are stitched together seamlessly and merged into a single 2D map product. It's been geometrically corrected so that scale is uniform. Features are in their true geographic locations so that you can make spatial measurements. A digital surface model, or a DSM, is another solid raster product where the pixel values represent your elevation. Related to that is a digital height model, which includes canopy height models. And in this, the ground has been identified and set to 0 elevation, and everything above the ground has a pixel value of its height above the ground. Then you get really fancy and start doing these textured 3D models. This is like what you would see with Google Earth if you zoom in and you can start looking at 3-dimensional buildings and trees. And you can do that with your own imagery as well. So that's kind of cool. So there's some different options you have available for software for running through these SFM workflows. We used to have a slide where we listed a few of them, and I realized that they were very obsolete. So I did a pretty quick Google search here and discovered that there's a lot out there. And this isn't even a complete list. Esri has a product called Drone2Map. They're the makers of ArcGIS. That's not on here. And neither is the Pixels to Points tool in Global Mapper. But as you can see, there's a wide range of prices for these products, from free, which probably are not very user-friendly, to fairly expensive, which are the more automated software packages. And within these, at least for the paid version, you can typically get access to trial and demo versions, so they're free licenses to test out the software, different levels of packages depending on your needs, educational discounts if you're a student or an instructor, as well as cloud processing options, so that if you just don't have a computer that can cut it, you can upload your photos to their server for processing, and then they send you that final product when it's ready. We use AGSoft here in the lab. We've had licenses for this for several years. Works really well, so we really haven't looked into other software, so we just haven't had to. So now for some technical specs about the imagery that I chose to analyze for the study. It was acquired by the James Sewell Company, acquired over 2 days, November 1st and 7th of 1977. So this is fall leaf off imagery. It covers central Penobscot County. So if you look at this tile index here, you can see the photos range from Alton down through Old Town, Orono, VZ, Bangor. There's 12 flight lines composed of 254 photos. However, there's one flight line that you see in the northwest corner there that's kind of removed from the rest, so I didn't process that because it wasn't connected. And I also had to remove a couple of photos scattered around the edges that didn't process properly. I ended up with 244 photos that I analyzed. For the photography techies, the camera was a black and white Zeiss model, 6-inch focal length, processed to panchromatic film at a scale of 12,000. Another way of thinking of this is that 1 inch on the photo equates to 1,000 feet on the ground. Here's an example of one of the photos. This is zoomed into downtown Orono, going up into the campus a little bit. And you'll notice that around the edge of this photo, there's a black border as well as some black marks on the sides and in the corners. And these are called fiducial marks. And I have to refer to my notes here because I'm going to get the wording wrong. But fiducial marks, they're optically projected geometric figures. They're located on the sides and corners of aerial photos. And they're essentially reference marks that define the coordinate axis and the geometric center of each photo. And they're helpful for orienting and processing old school analog photogrammetry products. And I'll show you what I did with them in a little bit. So as I mentioned, there were two different versions of scanning technology that was used with this particular acquisition that I wanted to look at. The first represents the photos that you can download directly from Fogler Library on Digital Commons. I believe you scanned them yourself, Kyle? Some were ready. Okay. Right. So these are, so 3,500 pixel resolution, and I was able to calculate that represents 78 centimeters per pixel on the ground. So below is an example from what Esri did, and I assume you mailed them the roll of film, and they did their own scanning process. They also did some photo enhancements too to clean up the imagery, and those came back at pretty high resolution, so 15,800 pixels, and each pixel in this case represented about 17 centimeters on the ground. So if we look at it more closely, I've zoomed into the main terminal here at the Bangor International Airport, and you can see some pretty good detail here. This is the Fogler scan, but you can definitely see some pixelation and maybe not so much detail looking at smaller objects like cars and markings on the ground. Compare that to the Esri scan, much higher resolution, and you can definitely make out some of those finer details if that's what you're interested in. So some of the enhancements they performed, cleaned up illumination, brightness, contrast, things like that. And really what I would say, they normalized the photos so that they were more uniform both within the frames and between the frames with respect to brightness and contrast and a few other things. So, you know, if you look at this bottom example here, that histogram all the way to the right, it's a pretty washed out image. They were able to bring that histogram more towards the middle, and now you can make out all those details that were really lost in the original photo. I also do want to mention that each photo had a slightly different resolution from one to the next, and this did pose a little bit of a challenge as I was processing. They're not all 3,500 by 3,500. Some of them were the same, but many of them, and this is just an example of some of those photos, and you can see that red column there, the resolution varies from one to the next, both with the library scans as well as those that came from Esri. So the structure for motion methods that I use aren't expected to handle these fiducial marks and borders very well. So I attempted to look into different methods of removing them, leaving just the photo to work with. And I did this in decreasing order of time and effort to see what I could get away with. So the first method I chose here was the magic wand method. And with this, Agisoft allows you to use a tool to click on a border, and what it does when you click on a pixel, it expands that selection to include other areas that meet a certain threshold of similarity, right? And this is the same tool that's available in other photo editing softwares like Photoshop, for example, has this option. So I did that with those border areas. Can't really see it in the example here, but there's a thin white line that separates the photo from the border, and all of that outside was masked out, retaining all of the photo information. Then I tried a quicker method where I just dragged a square box, making sure that I excluded all the fiducial marks and masking out all of that outside area. But you can definitely see that I did lose some of that, the area of the photograph itself. And what I found was when processing these photos, the overlap was reduced just enough that it didn't work properly. So I disregarded all of these. And lastly, I did the easiest possible thing, which was nothing. I left the border on there to see what would happen, see how AGSoft would handle it. There was a fourth option that I looked into. AGSoft allows you to leave the fiducial marks in. If you have access to the original camera calibration report, which thanks to Paul for supplying that, you can pull up all sorts of information from when the data was acquired, like focal length, all the different distortion coefficients, and all sorts of things. You can enter that information into AGSoft. However, because the pixels dimensions, they varied slightly from one photo to the next, I would have had to do that for each and every photo for both of the scanned data sets. I just chose not to do that. It wasn't worth it. So now I'll run through the different steps that I used in AGSoft, the workflow, and I'm sharing the parameters that worked well for me in case anyone else wishes to follow along and not have to go through all of the trial and error steps. I used a lot of the default settings. One that I'll mention that doesn't seem very important, but it ended up being very important, I think, is this last one. I excluded stationary tie points, and I'll explain that at the end. This figure here shows the result when all those photos were aligned with each other and stitched together. The black dots represent where the photos were taken. And as you can see, the colors here on the right, they represent how much overlap between photos is represented by any given area. So we have between 2 and 6 photos that cover any given area on the ground within the study area, which is pretty good. You can see in the middle there, one of their flight lines, the plane drifted a little bit to the left, so we lost some overlap on the right, but we gained a little bit on the left. So overall, they did a pretty good job for back then. So this next step here, what you're looking at, this is actually the first step in my model creation. This is the sparse point cloud using the Sewell photos of that central Penobscot area. But I needed to georeference it, right? So I have to give it that reference location so we can tie it to the ground. And to do this, you place ground control points throughout your study area. It was kind of hard to locate reliable spots that I could see both in 1977 as well as present day. I used Google Earth as my reference. Maybe not be the best source of reference information, but it's free. It's available just about anywhere, and the average person can access it and get this information out pretty easily. So I was only really able to find 10 points throughout the study area that I felt good about. I wish I could have used all of them as ground control data, but to do this correctly, you really need to set aside 5 that are used for verification of accuracy at the end. So I did do that. That being said, I chose the 5 best as my ground control points and the 5 that I have the least confidence in as my checkpoints. Here's an example of a ground control point, Sewell imagery up top, and I found a spot in the markings on the parking area in the southwest corner of the Bangor airport, and I had a pretty good suspicion that hadn't moved since 1977. I was able to count the cement tiles in that pad to see that it was the exact same spot. That was a pretty good ground control point, flat to the ground, so it meets all those requirements. And here's an example of one that wasn't so good that got demoted to a checkpoint. This is a spot in the Kenduskeag River. I found a rock in the river. I used that. It's not ideal because the rock isn't flat, so we really don't know what elevation the top surface is at. And it might move. I mean, it's a river, so flowing water, ice, things like that. So I had a pretty good suspicion that it was more or less in the same spot. But I used that as a checkpoint among a few others. So the next step is this dense point cloud generation. I chose high quality. What they consider high quality is really how your point density. You get to choose what point density you want to work with. And those steps change by a factor of 4. There's another a higher quality setting than high, but that really takes a ton of processing time and didn't really seem worth it. For the other settings, I used the default settings. And I also chose to classify ground points I'm not going to go into what those settings ask for. It's a similar process if you use other GIS software like Global Mapper. They ask for those same things, but those are the settings that work for me if anyone's interested. And here's what I got. So here's a dense point cloud. I zoomed into the campus, the South Campus area, and brown represents the ground points, gray is everything else. And I think it did a pretty good job using those settings of identifying what was ground and filtering out everything else. So to compare these different methods, I decided that building would probably be a stable platform that probably hasn't changed in height over the past few decades. Just out of convenience and familiarity, I chose Nutting Hall. For reference, I was able to get a hold of blueprints from some work that was done on Nutting Hall, thanks to Louis Warren. He dug this out for me. Just as general reference, converting the height that they have there in their survey, I get 8.23 meters. This isn't measured right from the ground, so there's certainly it's a little bit off on the bottom. And this also assumes that the landscaping hasn't changed over time, right, in terms of how high the ground is on the side of the building. So there's some assumptions I had to make. So I decided first to look at LiDAR, because that's the gold standard for 3D remote sensing data, right? So I used the LiDAR data set that was collected just this past summer from the folks with NASA with their G-Lite sensor. I overlaid this is a top-down view. I overlaid this on the ortho I created from the SUL imagery. Right off the bat, you'll notice there's two holes or depressions in the top of the building. No, they were not preparing to put swimming pools in Nutting Hall or anything, but I did reach out to the vendor, and what he told me that was because this particular acquisition was processed to optimize the rendering of vegetation and ground that was done at the expense of other objects, such as large building surfaces. However, just outside of those depressions where the roof surface does show up, it's expected that those points have a very high degree of accuracy within a centimeter or two. So I chose this corner of the building. Conveniently, that's where the Wheatland lab is located. And when I hovered my cursor over that point, it gave me a height above the ground. If you look at it from a side perspective here, of 8.65 meters. So that's how tall LiDAR says Nutting Hall is. I then moved over to the Esri enhanced scans. Same thing, top-down view. There's some gaps in the data. That's to be expected because you don't have as much overlap as you would get with, modern data sets or from LiDAR. But I could still find the top corner of the building there. And from this, I got 8.14 meters. I then tried the library scans. You'll notice that this is a less dense data set. That's just because the pixels are larger, the resolution isn't as good. But I could still find that same location on the building. And then I got 8.51 meters. So if we look at them all together, you can compare things like ground sample distance, centimeters per pixel. Doesn't really apply to LiDAR. But for the Esri imagery, 17 centimeters. For the library imagery, 78. Point density, points per square meter. Looking at all the points, LiDAR was pretty dense, 50 points per meter. The Esri imagery, 2.8 and half a meter, or half a point per meter for the library scans. I started those because those values I can actually change by changing the quality setting as I'm processing, but it's the ratio between those two that will remain constant. We can also calculate the root mean squared error. That's where those checkpoints came in. That factors all three dimensions, so X, Y, and Z in meters. For the Esri imagery, 1.7. For the library imagery, 2.9. And I actually think I probably did better than that, but those checkpoints were so questionable that I think that's why those values are pretty high. Because if we go down to the last row, the actual height that I was able to measure for Nutting Hall, we're within centimeters from LiDAR to the two different photo data sets. So that's pretty good, I think. So what's the takeaway message here? Put simply, using SFM software, the compressed imagery available from Digital Commons can be processed into 2D and 3D digital map products with a reasonable expectation of accuracy to make horizontal and vertical measurements from photos taken decades ago. It can be referenced to Google Earth, which, as I mentioned, is probably the most user-friendly reference product available, with little to no pre-processing. and the extracted heights are comparable to LiDAR, which is that gold standard. So if I had tons of free time, what would I do next? Or better yet, what would I suggest that someone else try to do? Perhaps sample some other areas besides Nutting Hall, some other objects. I did do a random sampling of a few buildings around campus, and they all were pretty comparable to LiDAR. Maybe try reprocessing these data with different parameters. As I mentioned earlier, an important setting that I selected was to exclude stationary tie points. And what this does is if the tie point shows up in that black border, that structure from motion algorithm is going to know that that point isn't moving from photo to photo, which is a requirement, right? So what I think by having that selected did was it automatically masked out that outside area for me without me having to do anything. Now, I don't know that this is a selectable setting on other software packages, so therefore I recommend maybe trying this with alternate software and see how it works. We could also try extracting your elevation values from LiDAR for georeferencing. Google Earth rounds to the nearest meters. They don't really have very good documentation, so I don't know how accurate that elevation information is. And it probably varies from location to location and from different dates of imagery. And also, if you do want to look at something other than just buildings, and you want to look at a forested area, you're going to have to get your elevation model from LiDAR because you just can't see the ground in the photos anyway. So you would have really no other choice. Some additional outputs that could be created. I did create all the mosaics. I'm happy to share those with you. And I think that's probably the most, that's going to be the most useful product for most people using these data. And really, what that gives you is the ability to visually see how the landscape changed over a period of decades. So that's pretty powerful information. And another thing that I think would be really interesting to look at, time series analyses, automated change detection, right? So this is kind of a nerdy remote sensing technique that's been around for quite a while that we use, primarily used with multispectral satellite imagery and multispectral aerial imagery, where you can track changes in the presence and health of vegetation over time. More recently, we started looking into using LiDAR to do this if you have repeat acquisitions, and this gives you really high resolution. This example here, we're looking at individual trees that disappeared between 2012 and 17, and then another period where they disappeared, as well as where vegetation has grown in. There's no reason you can't do this over a span of decades using this historical imagery. So I think that's really where the research potential will lie going forward to do these sort of analyses and similar analyses. And that's all I have. Thank you. And if anyone has any questions, feel free to reach out to any of us at the lab. We're more than happy to help you through if you want to look into these technologies and these methods yourselves.
Thanks, Dave. Any questions? And Dave, if you could put your mouse on the top of the screen.
Sure.
Anyone on Zoom have any questions? Feel free to unmute yourself or just drop something in the chat.
For what Paul spoke about as well, if anyone has any questions.
The overall questions that I have, but I want to talk about how. Well, I want to get a handle on the buffer up as far as collection products and so on, right? So, when you put the data, you show what they can do. Do they just do it like pro bono or for fun?
That rule is basically established. But what
are we talking about? Millions of dollars?
It's not, you know, keep across gallery, maybe
that. Comes out to about $700. Which is actually pretty standard, I think. There was someone they don't.
Well, if we can get too much closer.
Storage, so Kenny, just to your comment, we were just talking about the cost to scan the entire collection, and Paul was just saying that it costs about $700 per roll to have the scanning done.
Yeah, and one thing I failed to mention is that for the purposes of what I did, what you can download right from the library's website worked fine, right? But if you were interested in looking at that fine scale detail, like I showed with the airport example, then that's where that investment might be useful, and that's probably what most people would be interested in doing with it. But then again, the data sizes, you comparing one photo to the next, the compressed versus what Esri shared, I mean, it's a huge difference, right? So that would take up a ton of space.
You don't want visual comments.
Yeah.
You can't Dave, I have a question.
Yeah.
What are your thoughts on using just an off-the-shelf high-resolution camera to take pictures of these photographs and then move into a workflow like you demonstrated? Obviously on a project-by-project basis, you wouldn't want to do that for the entire collection. But might that be a way, rather than to have ESRI or some other vendor
So that
and a bunch of rolls, you could just try something like that?
I'd say that is an option depending on how you want to use the imagery. But keep in mind, now you're introducing a second set of camera distortions into this when you start processing those photos, right? So if you've got kind of like an off-the-shelf low-level camera that you're using, you might not even be able to process it with SFM software correctly and get good results. So that is something that I did come across in researching some of the previous work that was done. So a high-quality scanning job tends to be worth the investment depending on how you intend to use it. If people are just going to pull these up on a web page and look at what downtown Bangor looked like in the 50s, it's great for that. You could just take a photo with the camera. But to do this level of research, you probably would want something a little higher quality that isn't adding to the distortion that's already
So
there.
professional scanners.
Preferably, yeah.
That machine, the professional scanning machine, less than $250,000. But then there's time involved that you have to. Well, that's, I think that's. I guess that's my question. Apologies for coming in late, but if you had 140 grand for something in this space, is this the best use of this one? Right? Or is there something better that the digital archives get out of this? Right. That's actually one reason. Yeah. It's already feedback, but people that actually will.
Yeah, that's really up to the GIS community in general, right? Like what's most useful.
Yeah.
I mean, I'd love to say, yeah, get the best thing possible. We'd be able to use it. But again, in this little sample size of what I did here, what you did was suitable.
Yeah.
But there's a lot of detail that's missed in that other people would probably be interested in.
Yeah, I don't know, how. Like coastal. I don't know what kind of resolution they're looking for.
Right.
And maybe that's our next step is reach out to various stakeholder groups and see what people might be interested in. Would they be willing to contribute, you know, CFRU's membership style to, hey, let's get all of this scanned and we could use it.
Yeah, we did, I mean, responded to all the comments there. I also talked to Tora, down to units interested. But I haven't heard from them yet. This is a great start, you know. And, how it- so, new investors do this actually. Also, document. Yeah, you just need to get more input. This is great. Just you saying that, yeah, you know, yeah, there's a lot of post process.
Yeah, I have to say, I was surprised with how those results turned out, especially with the imagery that you scanned here on campus. And to be able to not bring in any other GIS layers and just georeference that historical data set and get within, you know, what, 10, 20 centimeters of what LiDAR said the height of the building was with no other input. It's pretty impressive, I think. Yeah. So the change detection, about that example that I showed in the forest there with the red and yellow and the gray colors, is that what you mean? No, so that was actually from 3 LiDAR collections, 3 really high quality research grade LiDAR collections from NASA Geolite, so 2012, 17, and 21. So that's actually why it looked really good. So that's where that change detection came from.
The roll, that one roll, getting rid of you also scanned that same roll with the camera?
No, actually, what I did is I took those images and I just reduced them. So, Photoshop says $3,500 one. That's why it's a little different.
Gotcha. Okay.
Yeah.
So I misunderstood that, but you did also scan some as well, just not for this particular.
Not that, yeah, no. But
Well,
you did samples of, you're right, there's like, kind of close there. So, you can track that in Photoshop. But I think some of those work pretty well too. Like the other one, Baxter State Park. So those, and those haven't been scanned by anybody. I did do a set just with that Canon camera.
Definitely.
So I'm trying, when I go, so I went to the website, look, and there's a lot, there's a lot on the website, and they have little shaped thumbnails.
Right, yeah.
For every one of them.
Yes.
How did you get those?
Oh, well, that's actually visual commons feature. I just upload the JPEG and it sets it up in the little viewer.
You have to get the JPEG somehow. You took a picture of the school photo.
Right, the ones I have actually, we got about almost 4 terabytes of stuff that was scanned at school. Oh, there's an aerial photo camera called the VX4000 that they had bought. It's technology circa. The actual, you know, the mechanical parts of it.
So the stuff that I see, when I can see the thumbnails, when I go on the digital commons, it's the stuff that school companies.
Mostly that, and then I take those and reduce them.
there's like 4,000 of those, you said, 3,000?
Oh, on that, on this cable, quite a few, yeah. It's,
So the stuff that it's not scanned,
right, that's most of it.
most of it, that's somewhere outside, you said.
Yes, it's our, storage facility.
So those, those are these catalog those, you can see like, yeah, where they
It's
take
the,
The-
they have an
yeah.
access database, it's a spreadsheet out of it.
So, I mean, I'm asking all these questions, but no, it's what I'm thinking at some point, we should get together like a, big group. To talk about potential applications. And if we have a particular application from coastal erosion thing, like some Baxter Fire, that's a cool one. We could then say, let's go into this access database, see what we have, and then prioritize what we get. Some of these are good science ideas. It could be part of the NASA project.
The other fuel, the 189,
I just went for it.
okay.
Yeah.
But I have those on that same drive, check out before.
Okay.
You want those?
Okay. Yeah, I noticed there was some more in there.
Yeah.
Coastal whatever.
Right? You can play off that, and I take the infrastructure you need to then. I think, at least the ones we're gonna there's so much money that goes back better and all that stuff, that's. That's not the big stuff, but I know that originally, so I was on that, luckily I got to be on the tour when this first was discussed and we got to go through the film road. On that trip with people, including Dan Knowles, who's a. She had ideas too about. Yeah.
No, yeah. So Paul, if I understand correctly though, in terms of the imagery that was either scanned already at Sewell or this collection that was scanned at Esri, all of the digitized collection is already available online. Or is there still some of that left to
I
go?
know there's quite a bit, but it's not.
Okay. But that, the remaining rolls of film that haven't been digitized by either of those entities yet, that's where you need the money to do it, unless you're just literally taking a photo of the photo
Right,
on the screen.
exactly.
Right, okay.
Which
Yeah.
you still need money to do, because you need someone to take the photo.
It has to
happen.
yeah.
It isn't free.
Right.
There's actually more of it later on, when you probably. There's probably a lot more left between the later stuff. So I feel like that doesn't really. You want to save the earlier stuff, but yeah.
And up until, I mean, even 1985, 1990, that's when all the USDS started coming out.
Form that.
That's the two part, that's another. Yeah, that's how they're very good.
Most of the data.
Little metadata inside the chemistry or something.
It's just in the base.
on the labels of the cans sometimes, like white lines or probably maybe.
But again, the database came from Sewell, right?
Yeah.
So there was someone within Sewell that,
Yeah.
maybe had a written record before, that would be the size that they understood.
Yeah, well, that's
Some
in the
contracts,
90s.
some not.
Even in the 90s, they went through it. You know, took their favorite out of it for it. Yeah, and I'll send that.
Yeah, that'd be good.
Louis, any questions? Louis, you still there?
We had 4.
Yeah.
I don't know.
Just a full room.
Yeah.
I don't know if it's here, but how, but it's. We used to always get this stuff, but people schedules and everything.